Hello. Yeah, thanks for the invitation. Yeah, so my name is Willy Döring. I'm the CEO of NeuroFox, and so my background is computational neuroscience. And so today, yes, I want to show you the Brain-Duino project. But before we take off, of course, I would like to give you a little introduction into the topic. What is actually EEG BCI? Is electroencephalography. It's a way of measuring potentials on the surface of the head. And so this had actually been discovered in the 20s by a German physicist named Hans Berger. And so here we are 100 years later, and we are able to control robots with the power of our thoughts. Or we can also explore virtual reality, navigate with our minds. And since over 5 years, there are also now consumer devices. So isn't this amazing? So who here in the audience has a EEG brain-computer interface? Is anybody here? Yeah, so it's not, it's still quite early maybe for a regular consumer device. So how does it actually work? We measure from different locations, and then we see those oscillations. Those are actually the brain waves, and you can analyze them through frequencies and looking also at the amplitude. And so, depending on where we put the electrodes, so for instance in the frontal lobe, we can look for decision-making processes, or we look at the parietal lobe on the top, basically, where you have motor planning, and also in the back of the head, you can infer visual processing. And so what kind of tools do we have at hand? So for instance, there's motor imagery. This is a way where we can detect if you're thinking about moving your left hand or your right hand, and trigger certain events with this. Then another technology is steady state visually evoked potentials, which is the way we can actually detect at which light source you're looking at by knowing the frequency of how it's pulsating, and it reflects also in the EEG actually. And then it's also possible to use it as a remote control. And so, like in this particular example, so like the P300, we can use it to scroll. So we cycle through different symbols, and if the one symbol you're thinking of is currently highlighted, it's possible to detect that and trigger something. And so the next there's neurofeedback. Neurofeedback is basically a way to train brainwave activity by the means of operant conditioning. So, and this can be seen in a way as a neuro enhancement. So it can be used, for instance, to learn mindfulness and also meditation. That's one way to do it. So how it works, actually, we read the brainwaves at the surface, then we do filtering basically. And so let's say you want to calm down, you want to have more, basically, very simplified, the slow brainwave activity. And so every time you produce more of that, you will actually get a sound. So that helps you actually to navigate towards those activity. And okay, it's also fun actually at different places. We made installations, and you can make also multiplayer games basically. So it's called collective neurofeedback. So you actually trigger sounds and visuals based on the group activity. And so of course, you can also use it for more serious stuff. For instance, looking at the cognitive performance, or also workload, like we just quickly talked about this in the introduction. A way maybe if something that you see is confusing to you, or is it overwhelming you, basically, this a way of analyzing it through workload. And also it can be used as a fingerprint. So, of course, but there's some limits, of course, here, and challenges, and of course the data can be very noisy. I can show you also in a minute, and so that's why, it's always a big challenge. And so the noise, of course, is based on how you put the headset, basically, and also you have factors like, let's say, loud conversation, something that disturbs you, and then also you have internal factors, like if you're very sleepy, this also changes the response, basically. So, but this is also a fun part for developers who are into machine learning, because there's always new things to discover, and this is still in progress, of course. So what is the basic setup? So you have the electrodes, then you have basically an amplifier, because it's a very weak signal, And so then you filter it and you also digitize the signal. So this is currently on the hardware side, and then on the software side you have things like machine learning, for instance, and further processing. And so I will start to talk about the Brainduino project, but I felt inclined to also talk about this. So how is the technology in the future? And okay, so speaking of last year, there was actually, university was able to show that you can control a prosthetic limb, each finger individually. For this you need surgery, so maybe I understand like not everybody wants to do that, but instead you could also inject electrodes with the neural does and monitor certain activity, but also basically control. And then there's neural lasers. Maybe you heard about this. Elon Musk is also currently investing a lot into this, like Brian Johnson too. The idea is basically to get an artificial cognitive layer on top of the current one, and being able to compete with artificial intelligence in the future. So this sounds a little bit crazy, but actually I think it's not so far-fetched. Also, if you're looking at what DARPA, for instance, is doing currently to actually restore certain memories at will, and also to strengthen the connectivity between two areas of the brain. And then there's also optogenetics, which is a way to control brainwave activity just with light, right? And so with this technology at hand, you can see that the line between humans and machines are beginning to blur. And also with the progress of artificial intelligence or machine learning, I think we can see that there's new technologies, new wearables coming up. And so currently it looks like GPUs is the thing to do, to look at there, but if you look at also what other companies are doing, they're building ASICs or neuromorphic chips, and they can do massive parallel processing, and being very power sufficient at the same time. So if you consider this, I think we will really see a revolution in wearables. And so we're moving actually all the software processing more to the hardware. And this opens up a lot of new applications. So especially in the interaction with machines. So like the human-machine interaction will basically be completely new in this way. We will have assistants that are able to understand us just amazingly. And this is because we're not only taking, of course, this one input, the language itself, but we're also taking into account physiological data. So not only brainwaves, but also eye tracking, for instance, or movement patterns. And so this is actually, I think, one of the exciting things to see also emerging in the future. So moving also from cloud services, like if you want to do some cognitive processing through clouds, it's going to be also decentralized. And you will have devices that can perform basically magic. So, all right, enough of that. So let me just talk about the Brainduino project actually. And okay, so it started actually 2 years ago, but also for a technician, it started almost 30 years ago. So he was building the IBVA, one of the first mobile-brain computer interfaces. And then we made it the Brainduino actually, so it's the newest version. And so we already have the Brainduino as an Arduino shield, and a lot of users are already happy with this. And now we're working on using also the Arduino Pro Mini, and also splitting the parts and making everything work actually as a headset. And so yeah, what the result is basically an EEG device that is very affordable and has very high data quality. So, and this is an open source project. And okay, so what can we do actually? We have the Brainduino, then we have a serial stream, and you can use different software to process the data. There's open source software like OpenVibe, and we're currently working on NeuroFlex. So there's still a little cleanup happening with the code right now, but it can be also be found at GitHub soon. And so what you basically want to do is signal processing, of course machine learning, and then you have outputs that say something to visualize with Open Sound Control or OpenGL, of course. So this is the basic idea. And yeah, like I said, how to participate in this project. We have a Slack, and GitHub, of course, and if you make it to Berlin, you're also welcome to join the meetup group there. So both on the software side as well as the hardware development, we're looking for people to help us with this, but also for design and also for neuro games, the things that make this whole project fun. And yeah, I would be happy to talk to you about this. And so what's the status quo? So currently we are we're actually manufacturing the first 100 devices. And so there's like a pilot test for those people so people can actually apply for one device. And and at the same time we're developing the software, really making it nice, usable, and like I said, push it to the GitHub also. And so yeah, we're looking for developers, of course, people to participate in this project, and of course some funding. And yeah, so let's maybe have a quick look. Let's see if I can just make this. Okay. All right. Okay. So I'm just going to show you a little bit. So I heard like it's better maybe we do the demo tomorrow, but I can nevertheless want to show you something still. Okay, so let's give it a try. And so this is the software right now. And so that's what I also mean. So here we have actually the data coming in. Excuse the resolution. It's usually on full HD. So yeah, we have something coming in actually. And those are actually brainwaves. And we have different ways of also visualizing them. And yeah, and then we put this actually into a little game. It's actually a flight simulator, and I'm not sure if I can do this right now. Maybe I'm a little bit too stressed, but I can give it a try. So the idea is to make it able to fly higher if I focus on it really good. So give it a try. Second. Base. Okay. Let's see. Okay, right now. Yeah, so that's what I mean. Data can be noisy, but all right. Okay, maybe that's that's a way of showing it. Not also actually stopped. So that's very typical, maybe. Yeah, but maybe we can go over to the questionnaire. To the Q&A, and like I said, I would also really enjoy to show you outside the demo, and you can also try to run the flight simulator, and yeah, all right.
You know, you actually have a lot more time.
Yeah.
To show some. Is there anything else you can show?
Yeah.
Let's see you stressed out.
Okay, this is actually maybe. Here, 1 second. All right. Yeah. So.
How do you know you're stressed?
Okay, so how do I know I'm stressed? I can show maybe here you have the higher brainwave activity.
All right, I gotta make you stress.
Okay. All right, here we go. Well, yeah, just slightly, of course. Yeah, but I can maybe show what happens when I just relax for just
okay,
brief
relax.
moments. Okay, I'll try to relax in front of the crowd.
Doesn't seem to change.
Nope. But
no, you look more stressed.
Oh wait, no. Look at this. So, so the colors basically the dark red is very high activity, and the more it gets blue, and this yellow. So like this was the phase actually where I was just relaxing for a short moment.
Okay.
And yeah.
All right.
So,
any questions from the audience? Any questions from the audience? Great.
Yeah, I guess I have just a question about the raw data. So I noticed that it looks like it's coming in at a fairly low frequency. I was just wondering, like, what is that? I guess, what is the range of frequencies of interest when you're doing EEG, and what frequency do you sample at?
Sorry, the last part.
What frequency do you sample at?
Okay. So what's important is to have a range, let's say, between actually starting at 0.1 hertz and then going all the way up to 40 hertz, 50 hertz or something like that. And so like the most common activity you have actually between 0. Something to 40, and that's why we also made like a bandpass filter here. So you can see right now the filter mode is on, and so it goes roughly also only to 40 hertz. This is really also where we want to look in particular. So, but of course we sample more. So it's not only it's not like 80. So you have the Nyquist theorem, you have double the samples, but we can go up to 1,300 samples per second. And this is also great also if you want to do, let's say, classification if you have a lot of data points, and also for discerning between, let's say, noise and the actual brainwave signal. Yeah.
And I guess what signal or what techniques do you use to process the brainwave? So, like, I assume you mentioned a couple of different utilities, but what's kind of the most common thing to use?
Utilities? You mean like a pipeline of processing, or? Yeah. So basically, you have what you do is because also you have effects like the DC drift. So because of this, basically how it works, how the reading, and so what you want to do is it's called like a DC drift correction or a baseline correction. So you bring it to actually, as you can see also in the raw data plot here. So you see that it's kind of moving up and down, and so this is actually what we first have to do is to basically remove like an average signal value. This is baseline correction, and then you do also filtering, and so something like bandpass filter. What we currently use is like Butterworth, and you can say, okay, I want to start. So like in this example, we start around 0.5 and then go all the way up to 40. And so then the next thing, depending on the task, of course, for the P300, for instance, on the one hand, from the application, you're showing some image. Let's say one example is maybe with people that you know or people that you don't know. So so you know the exact moment when you are showing the image, and at the same time you're having a little data window, you're tracking the brainwaves, and that gives you actually the way to put the samples actually into a different processing. Like for instance, you can put this in support vector machines like the older technologies, but you can also actually use something like TensorFlow, like for instance WaveNet, because it's basically waves. So you can treat it the same way you treat audio, and that makes it also very interesting, I think. And yeah, so like this is one of the things how I would say you can work with this currently with using current technologies. Yeah.
Thank you.
Yeah. I have a question here. Hello. Please don't take photo. Thank you. Yeah, I have a question here. Because thoughts are running simultaneously in the brain. So on the subject of stress, one has positive stress and negative stress. And on top of that, because you have a lot of people, for instance myself, I can think of like 20 tasks at the same time and even go down to details. So some tasks have a lot of positive stress and some have very negative. So my question here is, how many channels you can have, and how do you do the arithmetic between the different kind of stress? And also, I'd like to know a little bit more on your filtering process. Thank you.
Okay, so yeah, different kinds of stress. That's actually a good question, and one has to, there we have to look a little bit deeper also, of course, in the data, because they can, of course, be different unfoldings, and actually, if you want to classify it, it may look the same to some extent. But if you, for instance, look at the phases, so you not only have the frequency and the amplitude, but you also have a phase, like, you know, the positive phase of one wave, and then, for instance, what you can do is you can look at the synchrony. You can look at how much is the left and the right hemisphere synchronized, this gives you like a different interpretation possibility. So, like let's say a positive stress would be if you have a very high synchrony there, so like a de-stress. And on the other hand, if you're stressed and let's say you don't know what to do or something, then it's different. Then you have more like a chaotic, non-synchronized activity. But yeah, so this not. So yeah, depending on the software that you use, of course, those kind of overlapping or let's say statistical errors can happen if you don't consider something like this. Because if you just look at the amplitudes, okay, it looks like, oh yeah, the beta waves are rising, and oh yeah, okay, this is probably stress. But yeah, you're right, this can also be actually a process of something positive. Yeah, and so with the Brainduino, we can go up to 16 channels with the unipolar measurement and 8 channels with bipolar. So currently what I'm using is one setup with 4 electrodes, and so also with this setup right now, I could also look at the synchrony. And yeah, sorry, I didn't understand the last part. Was something about the outlook, or? Oh, sorry.
All right, we only have time for one more last question, okay?
I had a question. So, I wanted to ask, how many sensors is your setup using? So, many other devices that measure EEGs, there's something like the NeuroSky, they have just like one electrode that's placed on the forehead. So, is the Brainduino using more sensors, and how accurate is it?
Yeah, so we use, so right now for this, yeah, there's like devices that only use one sensor. You can do certain tests, of course, you can do like this very simplified, yeah, like looking at the arousal stage, like how awake am I, or am I sleepy, have I been drinking coffee, and so on. And so with the Brainduino, we have 4 electrodes at hand, and we want to differentiate basically in the prefrontal cortex between the left and the right hemisphere. Yeah.
So, but like the EEG machines which are used in the medical industry, like the hospitals, so they actually have an entire like cover kind of thing, and they have like multiple electrodes. So how accurate is your measurement while taking 4? Because they kind of have one electrode per lobe of the brain.
Right.
So,
yeah, so like if you want to do, of course, if you want to do the basic research, if you want to find out about processes maybe that are only theory currently, of course, then you would look for a cap in that way. But there actually right now, there's research emerging that is showing that you only need a few electrodes, and you can already make a very precise interpretation there. And also, yeah, according to the signal quality, this is also what is basically comparable to medical devices that we can offer with Brainduino. So one of the applications, for instance, what they're currently looking into is a way of also bringing in stimulation, sensory stimulation, and therefore you don't need actually the whole cap. It's can be done with a few electrodes. Yeah, but I can also tell you more about this later. Sure.
okay, thank you.
All right, with that, thank you very much, Willie. A round of applause for him on EEG. Very interesting project, Brainduino. Hope you guys are interested with what the possibilities are for the brain-computer interfaces. Last year, in September 2017 to February 2017, FOSSASIA organization held a cold heat contest to actually encourage more developers to be involved and contribute to the FOSSASIA project, open source projects.